So,
Matthieu?
yeah.
Oh, sorry, just started the recording. Just a question: what type of audience are you presenting this to? Is it students? Is it?
It's very simple. It's going to be for doctors that I mean, this is to try the material today, but I'm not sure you're going to learn very much, Paul. To be honest, I'm going to explain Q learning and deep Q learning.
No. It's more to help you have the best session possible at UCSD.
Oh,
what kind of people are you presenting to at UCSD?
All right. Yeah. So they're going to be doctors. I think most of them medical.
Okay.
I think some people will have experience with machine learning, but I suppose more supervised models.
Yeah.
All right. So I'm just going to share this. Very simple. So what we're going to do today, again, this is very much to try some material that I've put together for a workshop. The workshop is going to be an hour and a half, so a bit longer than what we have today. But my goal is to introduce some the fundamental concepts behind reinforcement learning and to show some examples, coded examples using a Colab notebook, Python, and the OpenAI Gym environment. So all virtual data. There's no time or no scope really to use real patient data in a quick tutorial like this. But so I have a few slides to start with. Okay, the very basic thing I want to introduce is to start from the very beginning and to say that machine learning has basically three big pillars: supervised, unsupervised, and reinforcement learning. And more or less, we're going to forget about the first two, and we're going to focus in this little tutorial on reinforcement learning. Here, what we want to do is to model and to learn an optimal decision strategy. And I'm taking the analogy of a rat in a maze, and this is very much what we're gonna end up doing in the computer exercises, which are basically to train agents in virtual worlds that we can call grid worlds. So basically you have an agent that can be in different states of a system, and in each state the agent can take actions, and the action is going to influence their probability of transitioning to further states, to future states. And the goal is to end up in states that have desirable properties, and to avoid states that are associated with penalties. So here the rat could be interested in reaching the cheese rather than reaching the electric shock. And again, if we make a really crude shortcut, we could put this in parallel with healthcare and say that patients can be in different states of disease and health, and our role as carers and clinicians is to treat them, to influence their probability to transition, hopefully to healthier states, and eventually to discharge, going back home alive rather than dead. But the objective could be other. The objective could be, for example, to improve organ failure, or to shorten the length of stay, or to reduce the cost of a particular treatment. So if we formulate medical decision as a reinforcement learning problem, here we're going to analyze the interaction between a physician and the environment of the patient, you know, the physiological environment. We act on our patients by usually giving them medications, or taking them to surgery, or by doing medical interventions, basically. They react by switching state, that the physician observes the new state of the patient. And again, if that new state is better, then the physician gets a reward, and the action that led to that transition is reinforced. If we are able to define a problem in this fashion, we can basically do two things that are interesting. One is to quantify the quality of the physician's policy, and then to try to assess, to estimate an optimal policy that can potentially be different from what the physicians did. There's another important quantity that we need to define, is the Q value. So that's the action value function. formally called the state action value function. And this is a number that represents the value of taking the action A while in a state S. And you understand that if that's basically based on the future expected discounted reward that taking the action, this particular action, will generate. And if our goal is to maximize that reward, then it becomes very simple to find an optimal policy if you have a Q function that is learned and trained and converged. Basically, you just have to take the action that has the highest Q value in a given state, and that, according to this definition, will be your optimal action. The simplest way of deploying reinforcement learning algorithms is to build an MDP, a Markov decision process. It is interesting in our particular problem of medicine, because MDPs, they work really well for problems that are complex, that are stochastic, partially random, dynamic, and I think this very much applies to a lot of the medical decisions that we have to take. If you want to build an MDP, you need a set of different parameters. You need to define states. So, for example, health states. You can think about the cells in the grid world. These are states. Then actions, they could be taking different directions. The transition matrix, some models require a knowledge of basically the dynamics of the system. What is your probability of going to state t+1 if you're in state, if you're in a given state at time t and you take a given action at time t? That's the transition matrix. And then the reward can be given at each step, or can be given at the terminal step. In the particular model that we developed for sepsis resuscitation, we were giving 100 points reward for survival and 100 points penalty for patient death. I didn't define policy, but a policy is basically a function that tells you what action to take when you are in a given state. So again, that's very simple. Here you picture a grid world where the action space is choosing a direction. Well, if your objective is to end up in this the top right state, then you can easily figure that this policy is suboptimal, that will not take you to the most optimal the reward state consistently. This looks like a random policy that basically sends you anywhere, and this would be most likely representing an optimal policy where you maximize your future expected reward. Two more definitions. The value function. This is very simple. It is a quantity that represents how good it is to be in a given state. So this is prior to taking actions. It is a quantity that basically represents the value of being in a state. And then the action value function is slightly more granular in the sense that it includes two parameters, the state and the action. And it is the future expected discounted reward for taking an action A while in state S, and then following a given policy pi afterwards. And the two of them are related by the policy. That makes sense, and I can explain that if that doesn't make sense. But if you sum over all actions and basically you end up with a value function, with your Q function and your policy. So how do we solve an MDP? There's lots of ways of doing it with different properties. A very simple way of doing it is from experience. So you start with a random or null Q table, and then you generate trajectories following a given policy, and you measure the reward that you obtain. And basically then you update your Q table based on the reward that you have observed. The most common way of doing this is by using the Bellman equation, which is given here. And you need a couple of parameters, but it is quite simple. You need a learning rate, you need a discount factor, and you need to have defined a number of elements from your MDP, as you see. But this is basically learning the Q function from experience, from observation, from generating at the beginning random trajectories, and then iteratively updating the Q function. Obviously, you need a simulation experiment to be able to generate those trajectories. That's not possible with observational data, right? When if in my research, for example, when we have a set of observations of patient data that is set, that was collected in the past, we cannot use Q learning to learn the Q function. So we have to tweak those formulas to achieve it with retrospective data. The next important concept is deep reinforcement learning. This was this came to light in 2015 with this very groundbreaking paper from DeepMind in London, where they were able to train an agent pixel to action. So the only input they had was the screen of an Atari video game, and then they trained agents using deep reinforcement learning, and they were able to train them and achieve suprahuman performance for most of the games without any empirical knowledge about the rules of any of these games, which was very groundbreaking at the time, and actually led this little startup to be acquired by Google for 400 million pounds back then. So the way deep reinforcement learning works, or deep Q learning works, is that you don't explicitly define the states, but what you do is you train a neural network to learn the Q values directly from the raw data and the action that was taken. So it's, again, it very much relies again on observation and simulation, and having a very large data set of trials to be able to learn that Q function. And this is very much what they did here with these video games. They had computers playing virtually playing those games for millions of hours cumulatively in order to be able to learn an optimal strategy. But again, here you don't specifically define, you don't learn a Q table, because the states are not explicitly defined. The states actually are represented by the raw observations. So since then, there's been huge progress in the field of deep reinforcement learning, with the game of Go, chess, Doom, StarCraft 2, and many other very groundbreaking applications. I'm gonna skip this one, but actually it's very simple, right? So it is difficult to deploy those algorithms as they are in the medical field, because the constraints and the characteristics of those two environments are very different. Obviously, in medicine, we cannot afford to learn by trial and error. It's simply impossible. All we are left with so far is retrospective data sets, of which we have a limited amount of training data. So currently, for example, with Mimic, we have a database with 17,000 patients with sepsis, which is not very big. It still amounts to about 1 million hours of data, which seems to be sufficient to train those models, but more data would be better. Also, the environment is not fully specified in medicine, you see, so I think this is an important point. Here, at any point in time, you have all the information you need on the screen to make the right decision, and it's very different in medicine. You know, what we have is heart rates, we have a set of vital parameters, lab values, and it certainly does not represent the entirety of all the biochemical processes that are happening at the level of each individual cell of the body. Right, this is what we would need if the environment of a human body was fully specified. That's what we would need, and we're very far from having this. So, despite all of this, there's been a number of applications of reinforcement learning in the intensive care unit, and this is a review from 2 years ago, and you see that there's a number of papers published looking at optimal dosing of medications or timing of interventions and so on. You see those sequential complex stochastic decisions. It's not treatment A versus treatment B. You know, we're not talking about a randomized trial. This is for sequential decisions. Here is an example. This one is about optimizing mechanical ventilation in the intensive care unit. And here the action space is tidal volume, level of PEEP, so positive end expiratory pressure, and FiO2, the proportion of oxygen in the mixed gas that you give to the patient. My particular PhD was on sepsis resuscitation, fluids and vasopressors in sepsis. And you see that we've made some good progress on enabling the data, developing some of these models, but certainly where a lot of the efforts are focusing now is on the deployment of those algorithms. That's certainly not the purpose of the topic of this tutorial, but that's I think very much where the efforts of the community should focus. Okay, so we're gonna look at 3 toy domains from the OpenAI gym. The first one is Frozen Lake. So this is a 4x4 grid world where you start in the top right corner. You want to end up in the top left corner. You want to land in the bottom right corner, and the path is dangerous because some cells are frozen, so you can stand on them, and some of them are hollow. There, so you would fall in the water. So these would be absorbing states that correspond to a penalty. The second one is interesting because to some degree it's kind of a hierarchical reinforcement learning. What you want to do, this is taxi. What you want to do is pick up a passenger. So the taxi starts in any random location in the grid, a 5x5 grid, starts in any random location. First, you need to pick up a passenger and then drop that passenger in a specified location. So, and that gives you, with the shortest amount of steps, that gives you the highest reward. So we'll solve these 2 with Q-learning, and then the third one is the cart pole. So the cart pole is an inverted pendulum, and the goal is to keep that pendulum balanced vertically. So here the state is defined by the linear position of the cart, the velocity of the cart, the angular position of the pendulum, and the velocity of the pendulum. And the action space is going left or going right. You see it's a much more complex state space with continuous states, continuous actions potentially. You know, you could go more or less fast left or right. So for that reason, we're going to solve this one with deep reinforcement learning. We're going to use deep Q-learning. Right. So please follow this link. We're going to jump into the Colab notebook. Or that link was also sent to you in the email. But I'm gonna jump to the notebook.
Can you paste it? Can you paste it in the chat?
Absolutely, absolutely.
Because for some reason, when I accept an invitation, the email gets deleted.
Oh, here's go. Is that big enough? Okay. So again, we're gonna try this. I didn't write most of these tutorials. I found them, you know, ready-made in different sources. So I don't want to claim authorship for those. But I think they're very interesting and very. I think it's a great exercise. Do I have to zoom in? Shall I zoom in a little bit? So
can I
yeah.
just ask a question, Matthieu?
Absolutely, yeah.
Will the clinicians in the audience have any experience with machine learning before this, or like have they been to hackathons or anything like that?
I think some will, not necessarily all of them.
Okay,
You think the level is too technical?
I think in 1.5 hours it might be a bit much to cover the deep Q learning as well. I guess I don't know, but we'll see how that goes.
Yeah, I mean, yeah, I totally agree, and that was one of the things that I wanted to ask you guys. You know, the reality is that the code is written. You click run, and you have nothing to do, right? You just look at the thing running.
So they just need to understand the concepts mostly, I guess. Really.
I suppose. Yeah.
Okay, cool.
Okay. Any other questions from anyone or comments? Okay. So we're gonna start with Frozen Lake. So we're gonna use the OpenAI gym environment. So please open the Google Colab. If you've never seen this before, it's amazing. It is all web-based. You have pieces of text and pieces of code. This particular Colab notebook is in Python, but I think it supports other languages. And the chunks of code are kind of grayed out. You see, so this is text, this is code, and also it looks like code. And if you click on the left-hand side, you click on Run Cell, it's gonna run all the cells in that particular box. All the rows in that particular box. So here we import a number of packages and functions. We define our environment as Frozen Lake. For the sake of simplicity, I remove the slippery feature, so the policy becomes deterministic. If the optimal policy is to go south, you're gonna go south, and you're not gonna end up, you know, in a hole. But we can try both. And then if you type environment.render, it shows you in a very simple text fashion the 4x4 grid world. So you start in the top left corner and you want to go there and you want to follow the Fs, and if you go into an H, then you die. It's the end of that particular trajectory. We're gonna define a couple of things to be able to run Q-learning in this particular application. So you see this runs without producing any output because it's only definitions. So we're defining the action size. I mean, actually, we can print this, right? We can check what is the number of actions in our MDP and the number of states as well. So we've got 4 actions, you know, top, down, left or right, and 16 states 4x4. Yeah. We're gonna generate 1,500 random episodes in order to learn our Q function. Here is the learning rate, the gamma, that's the discount factor, the maximum number of steps in a given trajectory, and then this is a bit more complicated. It's basically it's a factor defining how much more we want to explore versus using the optimal policy that we have learned at a given point. Does that make sense? So we're gonna start with an empty policy, and then it's gonna get better and better. But if we stop exploring too early, the policy is not gonna be optimal. So we need to continue to generate semi-random or partially random trajectories all the way through the learning. But at the same time, we want to benefit from from all the previous trajectories we generate while we learn the Q function. So make sure you run this cell, and then we're going to train the model. So if you look at this code, I don't know if you're familiar with Python, but what we do here, we generate. So we start. So we're going to run this for the total number. This is a for loop, so we're going to run this for a total of 1,500 times, and each time we reset the environment, we're going to start over with a new empty trajectory, you know, with a random initial state. And sorry, no, we start in the top left corner. Here we decide whether we want to explore or exploit. So explore is basically taking any action, and exploit is to use what is currently considered to be the most optimal action for a given state. Then we take this action, and then we're going to update our Q function, and this is the Bellman equation that we had in the slides. Yeah, so the Q for this state and action depends on this number, all these parameters. You have your learning rate here, you have your reward, your discount factor, and basically here you reduce the epsilon, because as it's written here, we want less and less exploration, and that's it really. See, it could not be simpler. So if you run this, it takes just not even a second, but I print at the end, the Q table that we've learned. So at the beginning, the Q table you see here contains only zeros, yeah? I'm gonna add this here. The Q table is empty. And the Q table is 16 times 4, yeah? It's the value of taking any action in any state. So that's why it's the same size as state space times action space. And then if we train this, so this is the Q table after training, and you see that basically for each of the 16 states, now you can identify one optimal decision, the one with the highest Q value. So I'm not sure which one's which, but one would be up, one would be down, one would be left, one would be right. And then what we can do is we can look at a given episode. So this one will give you a representation of the state space for each step. So you see, you start in S, then it says to go down, so you go down, down, and then right, then down, then right, and you end up in the goal state. So we have successfully learned an optimal function, an optimal policy that avoids the holes. Because that policy is deterministic, I suppose it's going to be always the same. It's always only 5 steps, and it's always the same trajectory that is taken. Yeah. Again, a very simple example of deploying Q-learning on an extremely simple grid world. Any question, any comment about this? Does it make sense? Is it understandable? Okay, I'll take that as a yes. The second one is the taxi exercise. So you remember here, we're going to use the OpenAI. This is the grid world, so 5 by 5. Some transitions are impossible, so there are some states where you cannot go. You know, let's say there's a building there if you're a taxi, and you have 4 locations. The taxi, I believe, can start anywhere in the grid world. First, it has to go pick up a passenger and then drop that passenger in another location. So same thing as before. So you see here, because we use the OpenAI gym environment, it's all pretty much predefined, but the action size this time is 6 because you have the 4 directions plus picking up a passenger and dropping off a passenger. So that's six actions. We need more episodes because it's a more complex environment. But the code is very much the same. We also use the Bellman equation to update our queue function. If you run this, it should take a little longer. We could display our queue function afterwards, but it's quite large. It's 500 times 6. Okay, 20 seconds. And now, if we just run one example, so this is after learning, right? So you see the taxi starts in this position, and then if you follow the yellow car, you see that it turns out that the passenger was in the R position. When the passenger is inside the car turns green, and then the car has to go to another location, which is G. Basically to reach, so successfully drop off the passenger in the appropriate location. If we start over, if we generate another trajectory, this time the passenger is in B, so you have to scroll up, yeah, to start from the top. Starts in B, pick up. You see here the action pick up is chosen, and then go north, go to Y, and to eventually drop off the passenger in the Y location. So again, that's the most optimal trajectory given this this subtask. So I think that's an interesting one, because if the taxi was to go to the drop-off location without picking up the passenger, the reward would be lower. They would still get a reward, but it would be lower. But the agent was able to learn that the reward would be higher if first the passenger was picked up. Any comments? I mean, I think it's very straightforward. We're gonna move to deep Q learning. So again, because the environment, I mean, the environment of the cart pole could be fully explained and defined, but it is a demonstration. Let's say that we don't have access to full information in a real world application such as medicine, and then the principle here is to approximate Q using a neural network, possibly a deep neural network. Actually, the one we're going to build is not very deep, it's just one hidden layer, if I understand right. And we're going to use, and as an input, we're going to have the patient, the model features. So cart position, cart velocity, and then the angle and the momentum of the pendulum. So the environment, it looks a bit like this. So you have the pendulum on a horizontal line, and then, sorry, the cart evolving on a horizontal line, and the pendulum that has the objective, the maximum reward is for balancing vertically successfully the pendulum, the inverted pendulum. I don't know. Can you check if you, so I mean, if I do this, it's going to say that it's already installed here. So I don't know if you guys also need to install Keras. So we're going to install a number of other packages for this particular one because of the deep learning nature. Also, it's a different source. We use OpenAI Gym again, Cartpool versus 1. This is an additional function that we define that will basically allow us to plot the learning of the agent over time. Okay, so you just run this cell again, and we're going to start with looking at what is the performance of the agent with a random policy. So if you click here, and then on the cell below, what we're looking at here is we're generating 150 trials. So what we're seeing is not the pendulum itself, it's not the card pull itself, but it's the outcome of each trial. So you have the reward on the y-axis and the reward for the episode number on the y-axis, on the x-axis here. And then this one on the right is showing you the score, the average score for the last 50 episodes. So we have a goal here to reach 195 points. So what you see is that the reward is quite random and quite low, way lower than our goal of 195 points. You don't see the pendulum, but you can imagine that the pole is doesn't stand up, doesn't stay up for very long. Okay, here we go. So you see the average reward is very low, is less than 20. All right. So what we're gonna do here is we're gonna train a model. We're going to train a model to approximate the Q function based on the model state. Sorry, the state of the world, the state of the card pool. The output of that neural network is the Q value, and basically that allows us to equally, that also allows us to identify an optimal policy. Okay, if I don't know if I can. I should probably have learning. If you, let me see. Okay. So here, the input is the different features of the model. Again, you know, card position, card velocity, and the characteristics of the pendulum. The output is the Q value for action going left or action going right. And obviously, then all we're left with is select the action with the highest Q value. So let's define this. Define our deep Q network. That's the main loop. Okay, and here we're gonna train the model. So we're only gonna generate 200 episodes. We have 50 hidden neurons. So it's as far as I understand, it's a neural network with only one hidden layer and 50 neurons in that hidden layer. I believe there's let's look at the number of states. Only 4. Yeah, okay. So that makes sense, yeah? The 4 parameters that I talked about. And here we go. We start training the model, 200 episodes. Again, it starts really low. At the beginning, it's completely random, right? And then progressively, the model learns what is the most optimal action given the state of the system. And we start seeing higher rewards at the 50. And if we keep going, we're going to see higher and higher rewards. And basically the rewards correspond to the pole standing, staying erect. Consistently higher rewards. Is it all running for you guys? So we're nearly there. We have some good examples close to the goal of 195, and here we go. So you see there's still some randomness, but you see that the trend, so that's the orange line, is going up after 200 episodes. Consistently the reward's really high. So I suppose if we were to look at those card pulls, the pendulum would stay up for quite a long time. Okay, and that took about a minute 30 to train. And that's it. Any comments, any feedback, any questions?
I have a question. So you mentioned in your presentation that MDP, right? So how do we see it being utilized here?
So actually with deep Q learning, you don't really need to define all the elements of the MDP. It's kind of you kind of skip a lot of the steps of building the MDP. So you don't need to define the states explicitly.
Okay.
Does that make sense?
Yeah, that makes sense.
You bypass all of this with a neural network that estimates the Q values given the state of the system and the action taken.
Okay, so like the states and the actions are what you feed into the neuron, right?
Yeah. Exactly. And the output is the Q value.
Okay, yeah.
Any other questions? I can show you. This paper that we wrote a long time ago now. When I went to Leo's lab in 2016, I met Anirudh, and he basically took the MDP and worked on deploying instead a deep reinforcement learning model. So if you wanna have a look at that paper, it will show you how you can use exactly the same framework, but in a real world healthcare application. Quite short, but you see here. Yeah.
No, finish. I want to make a general comment. So if you want to finish,
I'm done.
I would say so. As a general comment, I mean, it is. I mean, as Luis mentioned, it's quite high level, as in, and I'm a clinician. Although I have been doing some machine learning, I'm doing a PhD on it. Although in something very different, it's quite difficult to follow it all. And I knew something before reinforcement learning. I would say, especially all the slides on the formulas at the beginning.
Too quick.
I don't know. Yeah, they're a bit like gratuitous, as in the. I would go a bit more on the general idea behind things rather than spell out the formulas.
Okay.
And also another comment that I would do is once you explained how reinforcement learning works, I would then maybe do the tutorial or show some stuff, and then sort of go back and see how this can be applied to medicine. I mean, it's just an idea.
Yeah.
I'm brainstorming basically, because it might be once you've seen how things work on a sort of more of a toy version, then you can understand how trying to implement this on a medical sense would be complicated and why it's complicated.
Totally, that makes sense.
Because otherwise it's a bit all at the beginning, and it's
okay,
quite hard to follow.
I'm reshuffling my slides.
But I would keep it more sort of concepts wise.
Okay.
Even the definitions of all the state spaces and stuff. I mean, I don't know how. I was, of course, nowadays I'm capable of following those, but I'm wondering if it's as understandable.
But I find it hard to show some code with the Q value if I haven't explained it and how it's updated, you know.
Right. Yeah.
Maybe I can warn people, be like, okay, this is the one slide with formulas. Be brave. Maybe I'll keep it. But I have to explain, you're right. I have to explain a bit better. Any other comments, guys, or is it do you think the level of detail is excessive, or am I missing anything important? Okay.
I don't have much to add beyond Stefano's comments. I found the concept of deep Q learning quite difficult to understand when I first went through it. So I guess that was
better explanations there.
Yeah. No, well, I think your explanations are really good. It's just you've got so little time to do it all, and that it's if you were teaching a course on this, it would be great. But just in a one-off session, it might be hard for them. But I guess what you're trying to do also is give them a flavor for what's possible.
Yeah,
they're not going to be able to do this by themselves just after one lecture. But then it gets them interested, and they can experiment on the Google Notebook, and go from there. So I think if you frame it in that way, then it should be okay for them.
Awesome. Stop recording.